In the previous video, we saw AddressSanitizer can detect memory bugs at runtime. But we skipped the most interesting question. How does ASan actually knows that a memory access is illegal? The CPU doesn't know it, the operating system, who is a manager, doesn't know it. So where does this information is coming from for ASan? The answer is a clever idea called shadow memory. ASan keeps a second memory region called shadow memory. This shadow memory acts like a map of your program's memory. Instead of storing data, it stores information about whether the memory is safe to access or not. Every time your program accesses memory, ASan checks the corresponding shadow memory entry. And here's the clever trick. ASan does not store one shadow bytes for every program byte. Instead, one shadow byte represents 8 bytes of real memory. So if we can see here, let's say your programs, we can divide your programs bytes in 8 bytes chunk. 8 bytes. So this is your program's memory. But ASan stores only 1 byte per 8 byte of program's memory as a shadow memory, as you can see from the visuals also. This mapping keeps memory overhead reasonable. Instead of doubling memory usage, ASan only needs about 1/8 of the memory. And that is just brilliant. And each shadow memory tells ASan whether the corresponding memory is safe or not. Different values means different things. So for a particular shadow memory, there can be 3 values. As you can see from the visuals also, 0 represents for that particular 8 memory region is 8 byte memory region is fully accessible. Entries from 1 to 7 shows that partial access is allowed. And poison, negative values, it means access is forbidden, and that is poisoned memory. And let's understand what is this poison memory and why it is forbidden. So to detect buffer overflows, ASan surrounds allocations with red zones. And red zones are the memory regions that should never be accessed. That is we call that poison memory. ASan marks these regions as poisoned in shadow memory. And that negative values that we have discussed signifies that this is the poison memory in shadow memory. As you can see from the visuals also, that normal buffer that is valid is fine, but all the red zones are poison, and that we cannot access. And if your program writes beyond the buffer, it enters the red zone. And ASan checks the shadow memory, sees the poison, and immediately reports an error. So ASan actually checks for these kind of red zones. And if your memory, accessed memory, enters any of this poison area, ASan immediately reports an error. Now sometimes the last block of the memory is not perfectly aligned. Let's say you have assigned a buffer for, let's say, 10 size. You have defined a buffer size of 10. So as we see, ASan only covers for 8 bytes, right? So it is 8 plus 2 bytes. So it will need 2 bytes to map this region, right? So shadow memory will keep it like 0 and 2. It means first 8 bytes are valid to access, but in the next 8 bytes only 2 bytes are accessible and other 6 bytes are red zone, right? So let's say your program is 10 and we make it buffer size of 12. So first 8 bytes it can access, and after that only 2 bytes it can access, and the other 2 bytes other than these 10 byte, these 2 bytes will fall into the red zone, and ASan detects this only, right? The shadow byte value 2 means 2 bytes are valid in the final block. Now, when the memory is freed, ASan marks that region as poisoned. Once it's freed, it is poisoned. So if a program later tries to access that memory, ASan immediately detects a use after free. So this is the secret that we didn't understand in the last video, where I showed you like how ASan works and how it detects the use after free. So this is the way ASan detects that. Now, if we see the same example again, that use after free, and if we use the same command to run that and see the thing, and now you can see these all FA are red zone. Here you can see heap left, red zone. So other than this FD, all the other things are red zone. And once you have freed the memory marked as red zone, and then after you try to access, so it got the error and crash. Showed the crash is like heap use after free. So this is how it worked. Behind the scene, ASan has already marked this memory as poisoned. So when this write happens, the runtime check fails and ASan prints the detailed error report. You can see in this screen. And if we talk about the design, this design is extremely clever. It adds runtime checks but keeps the memory overhead manageable. And it allows ASan to detect many types of memory bugs. We have seen the example of buffer overflow also in the last video. We already saw use after free, stack overflow, heap corruption. All these kind of bugs can be detected by ASan. But we still skipped one important piece. If you think, how does ASan actually perform these checks before every memory access? The answer is something called compiler instrumentation. And this is very important term. And after you understand this, all the things, all the stories will make sense. In the next video, we'll see how the compiler secretly inserts these checks into your program. And remember, we'll keep it simple.